Welcome to the lecture series on probability theory. Already you have much knowledge that autocorrelation function, cross correlation function, covariance function, they are used to describe the behavior of a random process. A random process is as an ensemble or collection of number of time varying waveforms. It is already pre-known. So in that context, if I consider capital X of t, this as a random process, we can use various functions like Rxx of tau or Rxy of tau as two parameters along with Cxy covariance for describing the behavior. Random processes either can be described in time domain or in frequency domain. Why should we go for frequency domain description of a random process when time domain parameters are already available? Is quite simple. There are certain instances where we cannot be able to know a mathematical expression for the given random process or a given signal also. Let me take a case. We know average power of a signal is given as average power P equal to limit t tends to infinity 1 over t 2t minus t 2t x square of t dt. Sometimes it is also taken as limit t tends to infinity 1 over t 0 to t x square of t dt. If I am interested to estimate the average power of the signal, this is the expression. What it requires? It requires the mathematical expression for x of t. However, in certain instances, we cannot have mathematical expression for x of t. Take the case of noise. Noise is random in nature. Noise can exist in many forms, and we cannot have a mathematical expression for noise. In such a case, how to estimate the average power? Not only this, wherever we cannot be able to extract the internal or hidden information of a signal or a process, we need spectral information. That is why in this lecture, we talk about the spectral characteristics of random processes. Before proceeding so, let you reiterate, let you remember one more time that what is the meaning of a random process. A random process capital X of t is an ensemble of collection of number of time varying waveforms. Say something like x1 of t, then x2 of t, okay, x2 of t, x3 of t, etc. It is not 1 or 2 or 3. It depends on which experiment you are carrying out. In simple, if capital X of t is a random process, small x of t is called as a sample function of the random process. That is why you can say a random process is an ensemble of a collection of number of time varying waveforms, which are in turn called as sample functions. Okay, so what is our objective now? Our objective is to describe the behavior of a random process in frequency domain. Frequency domain description or spectral characteristics fundamentally need the knowledge of Fourier transform. Even though many other transforms are existing, Fourier transform is the fundamental transform. And for any given sample function or a signal x of t, the Fourier transform is generally defined as x of omega equals to Fourier transformation of x of t, which is in turn written as minus infinity to infinity x of t e power minus j omega t dt. This is the expression for Fourier transformation of any given signal. Similarly, if you have knowledge about Fourier transform, how can we estimate the time domain representation is as follows. Okay, let me write the other case also. Okay, I will write here x of t equal to 1 over 2 pi minus infinity to infinity x of omega e power j omega t dt. This is forward transform and this is inverse transform. Forward transform is used when you have time domain representation. Inverse transform is used when you have frequency domain representation. These two are the fundamental expressions required for the spectral characteristics of random signal or random process. Now, let us start with estimating the power for a single sample function and then extend the same to a complete random process. In that scenario, let us define let there be, okay, let there be a random process capital X or T. Within this random process, let there be a let there be a sample function small x of t. Let me just write like this. Yes, this is the description of the sample function. I am considering only one. Among number of sample functions, I am considering one sample function. Within sample function, let me take only a small portion. Say for example, uh, minus t to plus t. Okay, this is a portion. So what I call this as, I call this portion as xt of t. This xt of t corresponds to truncated version of the, this is truncated version. This is the truncated portion of the sample function small x of t, right? Truncation means a portion of the total waveform is taken. Okay, so how it is defined? The sample function is defined as, okay, it is equal to xt of t equal to simply x of t. No, it's a sample function only from where to where minus t less than or equals to t. This is the existence or definition of the truncated portion. Small x of t is the sample function. Xt of t is the truncated portion of the sample function. In such a case, the energy of the truncated portion can be given as minus infinity to infinity x t of t dt, which is nothing but minus t t t x of t dt. Okay, square, here also square. Why so? The truncated portion is not existing up to infinity. It is defined as, it is taken as from minus capital T to plus capital T. So within that period, it is equal to small x of t. So that is why E of t, energy of the truncated portion, is given as minus t to t x square of t dt. Or I can also write the same as like this. I can mention the same as, this is equal to, okay, minus t to t. This is also accepted, xt of t square dt, right? This is the estimation of energy in time domain. However, from the fundamentals of Fourier transform, we have a theorem called as Parseval's theorem. Parseval's theorem is meant for estimating the energy or power in frequency domain. So by using Parseval's theorem, Parseval's theorem, okay, the same expression can be written as below. By using Parseval's theorem, I can write the same as, okay, E of t equal to 1 over 2 pi minus infinity to infinity xt of omega square d omega. I can put a mod also, right? This is Parseval's theorem by using this. This is what energy of the truncated portion. If my objective is to estimate the power, we know relationship between power and energy is power equals to energy by time. So what I take, this is 1 over 2t minus infinity to infinity mod of xt of omega square d omega. What is xt of omega? Xt of omega is the xt of omega is the Fourier transform of xt of t, the truncated portion, small xt of t. Okay, if you have observed, this is 1 over 2 pi, 1 by 2t, again 1 over 2 pi. Okay, whatever power you have estimated, this is corresponding to only a portion of the sample function. This is not applicable to all sample functions, nor applicable to complete sample function also, right? Because a random process is collection of number of sample functions. What I have done, I have taken only a portion of the sample function. Now, how can I extend for the complete random process? I will make t tends to infinity. What it means? Previously, truncated portion is existing for a small part only, a limited area only. Now, as t is tending to infinity, I am estimating for all complete sample function. And what I do? I apply expectation operation and apply expectation operation to get the average expectation operation. So in such a case, what I will get, once I am applying the expectation operation, correspondingly, I am going to get the average power of all the or complete signal. Then the power of the random process can be given as Pxx, average power of random process, not truncated portion, is given as limit t tends, okay, 1 by 2 pi, okay, minus infinity to infinity mod of xt of omega square by 2t, okay, expected value as t tends to infinity, d omega. This is the average power of the complete random process. Now the term is now I just the term e of xt of omega mod square by 2t. The term e of xt of omega mod square by 2t. This is called as power spectral density, simply called as PSD, power spectral density. As I am talking about a single random processor, sometimes it is called as auto power spectral density. When there exist two random processes, capital X of t and capital Y of t, correspondingly, we call it as the cross power spectral density. So finally, power spectral density can be defined as, okay, power spectral density can be defined as Sx of omega equals to expected value of E of xt of omega mod square by 2t. This is the expression for power spectral density of a random process. This random process uh, can be single or sometimes it can be two. When two processes are existing, we can call it as the cross power spectral density. Okay, here limit t tends to infinity, okay, it will be as existing t tends to infinity. Now, in such a case, what is the expression for average power? Average power can be written as Pxx. If I substitute Pxx equals to 1 over 2 pi minus infinity to infinity Sx of omega t omega. So this is how we estimate the average power of a random processor in time domain and in frequency domain. Pxx is the average power. Sx of omega is the power spectral density. That is about estimating the power of a signal or a random process. Now let us slowly continue the same with two random processes. Let capital X of t and capital Y of t. Capital X of t and capital Y of t are going to indicate the combination of two random processes. Then we have to estimate cross power. So again, I am going to take here also two things. That is, let me just say, what is the same process, small xt of t, small yt of t. These are going to indicate the sample functions of the capital X of t and capital Y of t. And we have just seen what exactly is going to be the cross power. We derive now. Okay, so I will define how capital xt of t equals to x of t or minus t less than equal to t less than or equal to t. Similarly, yt of t equal to y of t for minus t less than equal to t less than equal to t. These two are the truncated portions. In the earlier case, we have concentrated on a single random process and estimate the average power. Now, our interest is to estimate the average power of two random processes, x of t and y of t. Both of them are in capital letters representation. So, in such a case, again, energy of truncated portion can be given as, okay, energy of truncated portion I can write as Et of t or simply E of truncated portion, but between two random process equals to minus infinity to infinity, again xt of t into yt of t dt. This is in time domain. Now, if I go directly to power of this one, power of the portion equals to, how can I take the power? I just divide this minus infinity to infinity 1 over 2t x t of t y t of t dt. This is the average power of the truncated portion. Okay, 1 over 2t minus infinity to infinity x t of t y t of t. Now apply for Parseval's theorem here also by applying Parseval's theorem by applying Parseval's theorem. How it can be taken as, okay, P of t equal to 1 over 2t minus infinity to infinity. It can be simply represented as xt star of omega into yt of omega t omega 1 over 2 pi, right? By using Parseval's theorem. This is the definition of Parseval's theorem, and 1 by 2t anyway existing. However, this power estimated is only for a finite duration, as in the previous case, because we are considering the truncated portion only. So for transform this limited power to complete sample function, what can be done? By making t tends to infinity, by making capital T tends to infinity. That means you are estimating the average power for the complete sample function and applying expectation operation, how it will become, we will see now. Okay, applying expectation operation. Now, simply the power will be for the entire class. It's called class power. Pxy equals to 1 over 2 pi 1 by 2t. I can take this also in the inside the integral. Okay, let me just modify this expression. Okay, 1 by 1 over 2 pi minus infinity to infinity expected value of xt star of omega conjugate into yt of omega by 2t with t tends to infinity d omega. Hope it is clear. This t tends to infinity is meant for making the complete sample function into consideration. Expected value is taken to consider all sample functions. Similarly, this is pxy. No, similarly, I can go with pyx also. What is the power induced in x due to y? That is cross power minus infinity to infinity expected value of yt star of omega into xt of omega by 2t with t tends to infinity d omega. Now, if I replace the cross power spectral density can be given as this is mod, of course, expected value of xt star of omega into yt of omega by 2t with t tends to infinity. This is the definition of cross power spectral density. Now, finally, the cross power Pxy can be given as 1 over 2 pi minus infinity to infinity Sxy of omega d omega. Thus, the power can be estimated in frequency domain as the area under the power spectral density curve. It can be power as cross power. What is the meaning of cross power? Pxy. It is the power induced in y due to x. Pyx. It is the power induced in x due to y. So in this way, we can be able to easily know that average power can be estimated in time domain. If mathematical expression is available, it can also be estimated in frequency domain. So that is in this class. In the next class, we talk about properties of power spectral density, both cross power and auto power. Thank you.